is not divisible by any xi. We're good. So these q's, so we have x3 squared, x1, x3, and x1 squared. These are all units in the ring because we're joining both x1 and its inverse, x2 and its inverse, x3 and its inverse. So these are all units in that ring, and so they're all irreducible. And so the only thing that's left is, well, time to churn out the sequence of polynomials for the g to see if things do work out. So we start with g sub k minus 1, so k is 4. So g sub 3 is f, which is x1, x3 plus x2 squared. So the first thing that we do is that we replace, so we have g3, and we replace x3 with q3 over x3. So here's g3, we replace x3 with q3, which is x1 squared over x3. So x1 times x1 squared over x3 plus x2 squared. And then g2 double tilde, here we want to clear out the denominators, and then we don't have any xi that's a factor of everything. So all we have to do is clear out denominators. So we get x1 cubed plus x2 squared x3, and then we don't have to, no power of qm divides that, so this equals g2. Okay, so one down. So next up is g sub 1. So once again, we take g2 and replace everywhere we see an x2. We substitute in q2, which is x1 times x3 over x2. So x1's cubed, that stays by itself, and then x plus x2 squared. So x2 squared goes downstairs, and we have x1 squared, x3 squared upstairs times x sub 3. And so here, when we go to g sub 1 double tilde, we want to multiply through by x2 squared, but then we also know that now we have x1 squared as a factor of both this term and this squared, so we better get rid of those. We better divide out by x1 squared. So we're going to get x1 divided by x1 squared, but multiplied by x2 squared, plus, let's see, get rid of the x1 squared plus x3 cubed. And once again, that's going to be g sub 1. And one last calculation, so g sub 0 tilde. So we replace g sub 1 with x sub 1, q sub 1 over x sub 1. Q sub 1 is x3 squared, so that gives us x3 squared over x1 times x2 squared plus x3 cubed. And so here we want to multiply by x1 to get rid of that. Then we have x3 squared. We want to kill off. So in conclusion, we can see that g0 double tilde is going to give us x2 squared plus x1 x3, which is exactly g0, which is exactly f. And that concludes the proof. So what can we learn from this proof? Well, the first thing is that, number one, this is just going through the small example.
Proof modulo the theorem.
Proof modulo the theorem. Yes. I mean, we are very much using Fomin and Zolovinsky's criteria as a black box.
And this can be taught to a computer, and you probably did already.
Yeah, and so the first point I was going to make, the first lesson we can learn is that once you do a couple of these, you never want to do them again by hand. They're just very long and tedious. But then the second thing, as Dr. Z pointed out, is that I mean, this is just doing algebra. I mean, symbolic algebra. There's nothing. It's very algorithmic, and so it's not that hard to. I mean, you do have to think a little bit about how you do it, but like you teach a computer how to factor. Computers know how to factor. They're smart. Use Maple's Bell and packages to do that. To divide, look to see if there's a power of q sub n that has to divide out by. Maple can do that, and so it's not that bad to teach Maple to actually carry out this proof. And so that suggested. Last spring in experimental math class, the topic was sequences, and so I got the following idea for a program for a project to carry out. And so basically, here's how the project ran. So we fix k, that's the order of our recurrences that we're looking for. Fix a maximum degree d. And then form all polynomials in x of 1 up to x of k minus 1 of maximum degree d, in which every term has coefficient 1. And so that coefficient 1 was just designed to give us some structure so we don't have to look at everything. Just, it cuts down on the number of cases that we're looking at. And I mean, every case that we've looked at so far has coefficient 1, so it seems reasonable to restrict ourselves to that. So for example, if k equals 4, d equals 2, we get the possible terms that we can use are 1, x1, x2, x3, so the constant term, the linear terms, and then all of the, so we can have each possible product, x1, x2, x1, x3, x2, x3, and then x1 squared, x2 squared, and x3 squared. And so we're going to have 2 to the 10th, because there's 10 terms there, so 2 to the 10th possible polynomials to look for. And so what we did was for each polynomial f, we calculate out what is the sequence that it gives when you start with all ones. And so when we just calculate out some of the terms, we calculate out enough terms to see, to get to the part where you're dividing by previous non-1 terms to see, if to try to truly figure out, is this integral or not? And obviously, if you reach a non-integral term, the sequence is an integral, so just chuck it away and you're done with it. But if it is integral, if it does appear to be integral, you calculate out enough terms that you feel comfortable. We then make the computer then conjectures, I bet that this sequence is integral. At which point if we conjecture that the sequence is integral, we then tell it to call this whole process to prove the Laurent phenomenon. And then
you also check the Laurent phenomenon.
And then
for you.
So how it works is that we're in the conjecturing stage is only checking integrality of the sequence.
So you can also empirically first check the Laurent phenomenon.
Right. But by actually calculating out the terms of this sequence.
Yeah, the first very terms.
The problem with that is that is very slow to do.
Because simple country.
Yeah. So it's something where it's not too bad. Like I can handle in usual cases where I'm just looking at the all one start for integrality. It isn't too bad for me to run 2 to the 20th cases on the machine in the lab. I wouldn't want to do that if I was looking at actually using formal variables. So theoretically, yes, you could do it, but in practice, it is too slow to do that. So let me pass around a couple of handouts. So this is so what I did was, have the computer just check out, first it conjectures which polynomials give rise to the Laurent phenomenon. It weeds out like stupid examples, stupid polynomials. Like if my polynomial is just 1, okay, 1 for my recurrence. Okay, every term is going to be 1. That's stupid. But so it weeds out stupid sequences, and then it weeds out polynomials that give rise to stupid sequences, and then it prints all the ones that it conjectures, it checks, and if it checks out, it prints it out. So let me pass around. So these are I had two things that the computer did. So in both of them, I'm fixing maximum degree d equals to 2. So that's just sticking with the quadratic case, just to fit in along with what's been going on so far. And then the printouts for k equals 4 and k equals 5, I believe. So those are polynomials with 3 and 4 variables respectively. And so
you already discovered Somos?
Yeah. So right on the right in that one, I think that's the 3 polynomial. Fairly up near the top should be Somos hanging around in there.
Yeah.
These are all integral?
Those all give you.
Yeah, the 5th. It's neat.
So
that how the Somos sequence could have been discovered.
Yeah. So if it's a little bit of the chicken and egg game, because if people don't if people don't come up with, if Somos doesn't initially conjecture, come up with a sequence, other people don't come up with all their sequences, and then you don't see there's all these ad hoc techniques. Maybe Fomin and Zelvinsky don't look for some sort of unifying technique to try to knock out lots of them. So yeah. Okay, sorry.
Degree 3?
Degree 3? I did briefly look at degree 3, especially in the smaller order ones, and so the computer can run just fine on those. I was a little bit more. It was easier for me to understand the degree 2 ones. Like I seem to have a better. I was better able to understand the structure there. To try to spot patterns. The issue with degree 3, so. Let's see, how many more, you're getting tons more terms to check. And so, I think you're going to have 10 terms that you introduce here for the k equals 4 case. So that's 2 to the 20, so that's about where I conk out in terms of computer power to check every single one of them. And so then if I try to go to k equals 5 or something, it's almost hopeless to try to do everything.
Yeah, I think it's all randomly chosen.
Right. Randomly chosen always, you can do that, or you can try to make human conjectures what's likely to give you stuff. But if I stick to degree 2, I can actually go out basically to k equals 7.
Has anyone ever discovered a Somos-like sequence of degree 3?
Yeah. Those definitely do occur. I personally find them a little bit less interesting, but yeah, that is definitely. Fine. So I have all of this wonderful data. So what do I do with it? So the next thing that I do is, well, for example, I might see that in the k equals 4 case, one of them that should be floating around is one that comes up as 1 plus x1 plus x2 plus x3 plus x1, x3. K equals 5, 1 plus x1 plus x2 plus x3 plus x4. This is another one on, so this one is on the k equals 5 case. And then in the k equals 6 case, I don't have that printout here, but one of them is 1 plus x1 plus x2 plus x3 plus x4 plus x5 plus x1, x5. And it's like, definitely looks like something's going on here. That we have, more generally, f is 1 plus the sum of, from j equals 1 to k minus 1 of x sub j plus x x sub 1 times x sub k minus 1. And so I was able to prove that using human methods, that for any k that works. I have the proof in case you're interested, but I
That's the new result?
yeah, as far as I know, this is a new result. But the very nice thing is that so it's a human proof, but yet it's computer aided. So I have one part of my program that I use to calculate to check the Laurent phenomenon conditions. I actually have it so that it will spit out the proof for me to see it, and so it gives me a sketch of the proof in the various cases. And from the sketch of the proof in small cases, I can sometimes, not always, but sometimes be able to kind of eyeball it and come up with what the proof should look like in
Is that the
bigger
first example
cases.
of an infinite family?
I'm sorry?
That's the first example of an infinite family of recurrences where you have arbitrarily long
I
order?
don't know. I don't know.
But the Somos-like paper doesn't have this as an example.
I don't think they do. So then it's like, you know, you can spend as much time as you want just staring at the results, trying to come up with new families and stuff like that. And I don't know, you know, it's almost kind of like, as for me, getting my feet was like, I don't know when you stop looking for new families and stuff, you know, what counts as interesting stuff. So I have a couple minutes left, so let me just wrap up with a couple of conjectures and ideas for further work. So I have so the first conjecture I have, and this actually goes to why I was most interested in degree 2 cases, is so what I call a symmetry conjecture. So if we're only dealing with degree at most 2, then and everything else I was looking at, so coefficients 1, that satisfies the Somos-like criteria. Then we have f of x sub 1, x sub 2, x sub k minus 2, x sub k minus 1, is we can reverse this, the polynomial is symmetric if we reverse all of the coordinates. So that's one thing that came up. Another question, so one question
You
is
mean all the
like,
successful cases had this property?
I'm sorry?
All the successful cases?
Yes. As long as you're only the case I was looking at, so only coefficient 1,
Yeah.
and then the maximum degree at least at most 2.
And
So
out of the 1024
Right.
potential things that you got there, or
Yeah.
you print out.
Yes. Yeah, and so that actually, if you're trying to push up to k equals 7, k equals 8, you kind of assume that's going to have that, you know, and that makes it, you're only checking ones that are likely to work. Really fast, I have no idea if you can do anything, but like, can you go backwards from, so Michael Somos, he first came up with these through a study of elliptic curves back in the 80s, and so I'm wondering, can you work backwards from, I don't understand elliptic curves well enough to know whether you can do this or not, but just can you go backwards from you know, Somos-like sequences with that are integral to elliptic curves, and then finally higher dimensional recurrences. So in the Somos-like paper, they prove some things about higher dimensional recurrences. I'm wondering, you could create a program that will automatically check this type of stuff for higher dimensional recurrences. So that's all I have. So thank you all for your attention.
Thank you. Thank you to get to answer questions in private. Thank you. And next.